and write it down because you were waiting for your printout. Oops. Just a little bit of review. We learned about the greatest integer function, which has these brackets. Okay, that's not the same as absolute value. What did the graph look like when you graphed the greatest integer function? Good. Okay, it should look like steps. These broken horizontal lines. They're not connected vertically. They're only connected horizontally. And we wrote down some things about making the graph that we wanted to know about the parent function. What we wrote down was that they look like steps, that the vertex or the starting point was at 0, 0, and then once we started, we drew the step to the right with the open endpoint. And then we made a note that all of our steps were 1 unit long and 1 unit apart vertically. Okay. So here's I start at 0, 0. I draw my step this direction. I make it a unit long. I make the next one 1 unit higher than that. Okay. And then I follow that pattern. And I can follow it in the other direction. We also talked about the fact that there's no arrows on this graph because if you connect an arrow to anything or you start drawing something that looks like a ray, it's going to look like a piecewise function that has a new piece there, but that it's implied or we assume, unless you're told otherwise, that the steps continue forever on the graph following whatever pattern that they have up there. Okay? Any questions about this part of it? Okay? So again, our goal today is to be able to take equations at the end that have numbers, all different spots in here, and to be able to just take this and change it up a little bit and get what the example would then look like without having to plug in points to the graph. Okay, but we got to learn a couple things to do that. All right, so the next thing we want to write down about our graph are these basic characteristics. So, domain. What's your domain of this graph? All real numbers, right? You can still plug anything into that function and find a point that goes on with it. What about our range? Okay, so it's kind of like all real numbers in the fact that there is no stopping point up or down. However, to be all real numbers, that means that there's a point on your graph that captures any specific y coordinate that you're trying to. Can you guys find a point on that parent function graph where the y coordinate is 0.5? 0.5. It like skips it, right? There's like the gaps, right? Like you have a step sitting at 0, so you can get y coordinates of 0. But then can you get any y coordinates between 0 and 1? No, there's no points there, and then there's one sitting at 1. So we skip a bunch of stuff. But there is a pattern of the numbers that we are sitting on, right? We're sitting on like -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, et cetera, in both directions. So what do we call those numbers? How would we describe them? What kind of numbers are those that we just listed? They are rational, but even more specific than that. Good. They're integers. So they can be positive, negative, or 0, but they have to be whole numbers, no fractional part, right? Rationals allow fractional parts. We can't allow that here. So the range is all integers. If you guys don't remember what variable stands for that, z, is it? Okay. But you could write integers. The z? Yeah, the reason it has an extra line is when you write the names of number sets, you're supposed to write them with capital bold letters. So if you see it in a textbook, it's like a dark, like swirly R, or like a dark, like special looking Z. But like as a human being person that doesn't have like font automatic, when you write it, drawing that extra line is like making a bold capital letter in mathematics.
When you're drawing like a 7 and then like an upside down 7.
Sure, or a Z and then you just put an extra line in it. Either way, whatever. It's like the R. Put an extra line.
Doing it right.
Okay, that's all right. As long as I can tell you tried, we're good. Okay, X and Y intercepts. Let's do Y intercepts first. Look at your parent function graph. Where does your graph cross the Y-axis? 0, 0. Okay. It doesn't hit the y-axis anywhere else. So just one y-intercept. Okay, x-intercept. Where does your graph hit the x-axis? At 0, 0. Anywhere else? 0, 1 is like open, so it's like not there, but that's just like an ending point. Right? What about between 0 and 1 on the x-axis? Yeah, like 0.5, 0.2. How many x-intercepts are there? A lot. Yeah, mathematically infinitely many, right? All those numbers between 0 and 1. So the best we can do here is just say, like, basically there's x-intercepts at all x values from 0 to 1. But notice I included 0 and I didn't include 1 because of the way that our endpoints are on the x-axis for that step. All right, and what's the slope like? Yeah, up 1 over 1. And it's kind of weird, like, it's kind of like a slope because it does overall kind of go like a line, but they're doing different things. So when we think about this slope of 1, in this case, you really want to think about it, like Blaine said, I think, like up 1 over 1, because you really want to think about this one being the rise, which is basically like how far vertically your steps are apart, and this one being the run, which is like the horizontal length of your steps, right? So like the rise is like the gap between them, the things you don't draw, and the run is like how long you have to make your step when you draw it. Okay, so a little different than lines, but still kind of looks overall like it's traveling in that manner. Right? Any questions about those things? All right, the last thing I want to point out is what you guys should know from Algebra 2. Okay, so I want you guys to take 30 seconds in your group and think about this. I'm going to erase all the stuff I wrote on it, even though you probably already saw it. All right, so think about this, or if this looks too complicated, you can think about this, if the B bothers you. Okay? And I want you to, in your groups real quick, just brainstorm for me everything you guys remember about what putting numbers in these spots does from Algebra 2. What kind of transformations it causes your graph. Okay? Are there translations or shifting? Are there reflections? Are there stretches or compressions? If you guys know any of that stuff, because I just want to get some feedback of what you know to see what to emphasize when I explain it to you right here. Okay? So with your groups, take 30 seconds, and then we'll just kind of get like information from everybody about what we know. What we didn't look at in Algebra 2 is that there could also be a number multiplying in here. Now, in absolute value, we just didn't deal with that number, right? If there was a number inside multiplying x with the absolute value bars, we just rewrote it, and we got that number outside the absolute value bars. Okay? We can't do that with the greatest integer function because the function rounds stuff, so the number is going to be different if you round it before you take out the 2 or after you take out the 2. So it's not as simple, which means this number sitting in here does stuff too, and that's something we're not as familiar with from Algebra 2. So, okay, I color-coded it for a reason, I promise. All right, first of all the stuff that's inside of here, the H, okay, so the H caused horizontal shifting, right? The B is also going to cause some other horizontal stuff, but everything that's happening inside the function, and it's happening to x before you do whatever it is you're going to do, like round or take the absolute value or take the square root, all of this stuff is causing some sort of, sorry, I'm out of space on my board, horizontal change. Okay, so everything inside of there is causing a horizontal thing. Something is happening horizontally. Okay, so you guys told me with the H, that's shifting left or right. But it can also happen here with the B. If the B is negative, what do you think happens? What happened when A is negative? It reflects. So guess what's going to happen when B is negative? It's going to reflect. The difference is the direction of reflect. So when A was negative, our absolute value went from facing up, and then all of a sudden it went facing down. Okay, that's a vertical change. It went from up to down. Okay. Everything inside the absolute value function or inside the greatest integer function is controlling horizontal stuff. So this is still making a reflection, but rather from going up to down, things are going from left side to right side or from right side to left side. Okay, so it's a little bit of a perspective thing. So if the B is negative, you are reflecting, but people would call this a horizontal reflection. And you can just make this note on the notes if you made them yourself, or in this, or if you're have the cosmic catalog thing. So it's a horizontal reflection. And one more note about how people say that. Sometimes instead of saying horizontal reflection, they say reflect over this axis, and they either say x-axis or y-axis. If I'm doing a horizontal reflection, do you think I'm flipping things over the x-axis or the y-axis? Okay, so you want to say x so bad because x is horizontal, right? But think about what horizontal reflection is. Things on the left side are going to the right side, and things on the right side are going to the left side, like flipping the pages of a book. What would I be flipping over on the graph if I'm changing something from this side to this side? The y-axis. So weird. But we need the vertical line to flip things from one side to the other. So really try to get the picture of, like, if I'm changing something from the left to the right, what am I flipping over? So this is actually flipping over the y-axis, even though it's a horizontal type of movement. Okay? The other thing that B is going to control is something that we call horizontal stretches, and we'll talk more about this, and compressions. Basically, when there's a number there, so whether it's negative or positive, the negative part causes the reflection, right? So besides that, if there's a number there, like 3 or 2/3 or something like that, you're not going to have your parent function anymore, but it's basically going to be like someone took your parent function and they grabbed the paper by the sides, because I'm going to do horizontal movement, and they either horizontally stretched out your graph or they horizontally compressed your graph. Does that change any of the vertical spacing? No. Basically, I would either be taking your, like, look at your parent function on your cosmic catalog for your steps. Imagine if someone grabbed the sides of the graph and stretched it out. What would be happening to your steps? Yeah, well, they wouldn't be getting wider apart this way. If I'm grabbing the sides and stretching them, what's happening to them? Possibly. But if I'm only changing the horizontal, what's for sure happening? They're getting longer, right? So if I horizontally stretch my graph, the step's getting longer. Does that make sense? Okay. The pencil looks like it made a longer step. If I take it and I horizontally compress it, then my steps are going to get shorter. Okay. That's what that number is controlling inside of here. Okay. The A value on the outside, okay, so notice all the things that I wrote in green, the K value and the A value, those things are vertical. Okay? So all the vertical stuff happens outside of the function. Okay? Outside of the brackets, outside of the bars, outside of the squaring, outside of the radical. All that stuff is controlling vertical stuff. Okay? So like in absolute value, you guys saw that when the A was negative, instead of opening up, it opened down. Okay? That's because for the A value, when it was negative, it was again a reflection, but it was a vertical reflection. So you saw something that normally faced upward, all of a sudden was facing downward. If I'm doing a vertical reflection, which axis is acting like my mirror? Which thing am I flipping my stuff over? Yeah, the x-axis, right? A little bit crazy, I know. I'm pointing that out because sometimes they won't tell you it's a vertical reflection. They'll say it reflects over the x-axis, and I want you to remember that means they're still doing a vertical movement. They're flipping it over that from up to down. Okay? The other thing that A is going to control is it's going to control vertical stretches and compressions. So you guys said slope. Slope is like this, okay? If I took your step graph and I held it at the top and the bottom of the page instead of the left and the right of the page, okay, and I stretched it out that way, your steps will still stay 1 unit long. I'm not changing how long your steps are, but now they're going to be stretched further apart, right? Like somebody would have to step up higher to get to the next step, okay? Or if I took it and I started squishing them together, the steps would be really close together, right? You'd be able to step on them very easily. Okay, so that's what it's controlling, that number there, how far apart those are. Is this okay with everyone? So in Algebra 2, as far as I know, you guys are supposed to be using languages like, how many people have heard stretches and compressions? I'm not saying you understood it. I'm not saying you got it or are an expert, but okay, someone taught. Okay, good. All right, so That's what that means. We're going to get more into that. For greatest integer function, if we can just really represent like what's doing horizontal stuff and what's doing vertical stuff, and we're going to do two kind of contrasting examples to see what the difference between them is, and then hopefully we can graph without plugging stuff into a chart, okay, just kind of knowing our parent function. All right? Okay, so you don't need the cosmic catalog page anymore, but you can keep it out if you want to see your parent function or if you want to refer to which parts are changing what in the graph. And then we're going to do a couple of examples. So the examples, if you have the note guide, are in the longer note guide. If you don't have the note guide, you're just going back to your page where you did some calculations, and now you're going to put these graphs on there. Okay. So what's the difference between 10 and 11? Nick? Okay, so, yeah, okay, other way around. So 11 has something in the spot that we were calling B, right? The negatives on the inside. What did we say negatives are going to cause? In general, when something's being multiplied by a negative, whether it's in front of x or it's in front of the function, what kind of transformation is going to happen? The negative is going to cause what? Does the negative cause shifting? Does it cause stretching and compressing? Does it cause reflecting? Reflections, right? Okay, the negatives are going to cause the reflections when they're multiplying stuff, right? So then the question is, what kind of reflection when it's in a certain spot? So, yeah, so when the negative's out here, we said it's going to cause what kind of reflection? Vertical, which means we're going to reflect over the x-axis, okay? So here's what I'm going to do. You guys don't have to plot the original one, but I want us to all see how it's going to happen. So in like this green color that doesn't show up too great, I'm going to plot the parent function, okay? So I'm not answering the question yet. Just remember, here's what our parent function looks like. 1 unit long, 1 unit apart, right? Fair enough? This is our parent function, okay? All right, now let's think. If we are reflecting over the x-axis, okay? The x-axis is our mirror, and we're reflecting things that are over that to below it, and things that are below it should now come above it, okay? So first step is on the thing that I'm reflecting over. Well, if it's not any units above it, it's not going to get pushed below it. It's going to end up staying right where it is. So this first step is going to end up staying because it's on what I'm using as my kind of reflective tool, okay? This step right here is 1 unit above the x-axis. If I'm doing a vertical reflection, anything above the x-axis should get flipped over and should be below the x-axis, but I shouldn't change any distances. So I shouldn't change anything horizontally, and however far it was above should be the same distance it is below. So if this step was 1 unit above the x-axis, I should now draw it 1 unit below the x-axis, and I will have performed a vertical reflection. Okay. So this is going to be there. Yes. Okay. So this step here was 2 units above the axis, which means if I'm performing a vertical reflection, I should redraw it 2 units below. It's just like I'm taking my paper, folding it over the x-axis, and tracing where these things would have ended up. Okay. This one that was 1 up. So if I took this and I just folded it, this green little step right here would land right here. Okay? All right? So anytime you're doing any vertical reflection, so this next one's 2 units away from the x-axis, I'm going to redraw it the same way, but 2. So anytime I'm doing a vertical reflection, anything that's on the x-axis is going to stay there. Anything that was above should show up below, just like you folded it over, so the same distance. This step was 1 unit above. It's right here 1 unit below. Okay? So the green is not my graph. The green is not what you should have written on your paper. Okay? That was the parent function, and I was showing you how the reflection would work. Clementina? Yeah. Grant, your job is to hit Nick every time he falls asleep. Okay, got it. Sorry, we were trying to accommodate some other things, but this is fine. We're just going to have people wake Nick up every time he... What's that?
Yeah, Grant was on the news.
Oh, I heard about it. We'll talk about it later. All right. Okay, next thing, also a reflection. What's the difference between the reflection that's happening in number 11 and the reflection that happened in number 10? Good. This one's horizontal. So again, you guys only have to draw the end result so you can kind of see the difference from the parent function. But I want you guys to see how it's happening because in future things, it's going to be important for you to be able to do it yourself, okay? So again, in the green color, I'm going to put the parent function. So this is not the answer. This is what I'm thinking about what's happening to the graph. If this is the original step parent function for greatest integer, and this is supposed to perform a horizontal reflection, meaning things are going to reflect over the y-axis, and if they're on the right side, they're going to get flipped over to the left side, and if they're on the left, they're going to get flipped over to the right. Okay? So again, if anything's on the thing that you're reflecting over, it just stays there. So we have 1 point that's on that, so it stays there. Okay. See how from this point, this used to go away to the right? If you folded that over to reflect it horizontally, what you're going to see is the step go out this way and have that open circle right there, right? Just like I folded the paper over the y-axis or flipped that from the right to the left or left to the right, okay? So this next step right here, it starts 1 unit away from the y-axis. So you're going to do the same thing. You're going to start it 1 unit away from the y-axis on this side. And just like you folded it over, that's where that step would end up. Okay? This one that started 2 units away is going to start 2 units away over here, okay, and go away from the y-axis. Okay? Notice that if I folded them on top of each other, they would all lay on top of each other. That's how the reflection is happening. Okay? So this one here has an open endpoint on the y-axis. That's on what I'm reflecting over. That's not going to change. Okay? But the step used to go to the left of that with the open endpoint here, so now it would look like it goes to the right with the open endpoint there. Okay? This open endpoint started 1 unit away from the y-axis. This will on the other side. It went out towards the left. This one will go out towards the right. Okay? So there's how I've reflected all of those points. Okay? So again, the green was me thinking. That was my parent function. Okay? It's not part of your final graph here. Right? So 2 things I want you to gain from this. One is how you actually do a reflection. If you have something on a graph, can you reflect it over the x-axis or reflect it over the y-axis? Because that's going to be really important to us in the future. Second thing I want you to gain from this is look at the effect that it has on the greatest integer function for the current moment. You're graphing these. So when you see something show up with a negative on the outside, you should expect your steps to still be a closed dot. But the overall picture of it doesn't look like you're climbing up steps. Instead, it looks like you're climbing down. Okay? When the negative is on the inside, you make your closed point, and then do you go to the right like normal? No, the steps go to the left, and the end result looks like it's sloping down. So the negative on the inside is a little more complicated, right? The way the reflection worked and ended up, there's kind of more changes happening here than there are in this one over here. Okay? So, again, purpose, so that you guys can kind of distinguish what you need to know now and stuff like this. We're going to be graphing these now. So if you can just hang on to, okay, If the negative's on the inside, I got to draw my step the other direction. I got to make sure in the end it looks like it's going downward. If the negative's on the outside, I can still draw my step how I normally do, but I still got to make sure in the end it looks like it's like negative sloping instead of positive, okay, for right now. In the future, the way I demonstrated the reflection is how we're going to be using that idea, all right? Okay, any questions about the reflections? All right, so the last one we're going to do before we do one where we try and do a bunch of stuff together, and again, we're going to try and do it without plugging in points and just kind of walk through each change so that it's fast for you guys, is we want to look at the vertical stretching and compressing. What is the difference between when a number shows up here versus when the same number shows up here? Okay? So here's what I want you guys to do in your groups for me. We're not going to fill out t-tables every time we graph. Can you make a t-table? Absolutely. Okay? Is it going to help you? Probably, because you'll know where points are on your graph. But if this gets really complicated, you might not always choose the right numbers to go into the t-table to see every endpoint of every step, and it might get confusing about like how long your steps are and stuff like this. That's why we want the shortcuts. But for right now, if you guys could, in your groups, make a t-table, and I want you guys to plug in -1, -0.5, 0, 0.5, and +1. Okay, to each of these functions, so that we can see what the difference is and that you guys can practice your greatest integer calculation. Okay, so you're plugging these 5 values into each of these. The difference is, in number 12, you're going to round, and then once you're done rounding, you're going to multiply by 2 to get your answer. In number 13, you're going to take your input and multiply it by 2, and then you're going to round after you've got the answer. Okay, and we'll see if those look any different. All right, so you can talk to the people in your group, make sure you guys get all the right things. You can use ours. If you have results, compare. Okay, so look at what happened here. Okay. When I plugged in -1, I ended up with an output of -2. But when I plugged in -0.5, remember, it would get rounded to -1, and -1 times 2 would still be -2. So -1, -2 is here. When I plugged in -0.5, I still got -2. That tells me that that point is still on the same step, lined up with this one. It didn't create a new step. Okay? But when I plug in 0, that's going to give me a new step. Okay? When I plug in 1/2, it's also 0, so it's lined up with that one. And then when I plug in 1, I get 2. That's going to be a new step. Okay? So what I'm getting here is this graph. How is this different from my parent function? Okay, good. So this 2 showed up in our equation, and now the steps are how far apart? 2 units apart. That's happening because of this, okay? This number out here, and we said the number that shows up out here, if it was negative, it was a reflection. We already covered that. But the number part of it, okay, is either a a vertical stretch or a compression. Was this a vertical stretch or a compression? A stretch. It stretched the vertical distance. Normally it's 1. It got stretched out to be 2. The way that it did that, it took the normal amount and it literally multiplied it by the number you see here, and that gives you a new amount that is now the vertical distance that your steps are apart. Okay? So for steps, the number will always be it because our parent function always starts with 1, and 1 times anything will just be the anything that you get here. Okay? So this is called a vertical stretch. What was that, Nick? There isn't one in between. What's happened is there's just a larger gap here. Okay? Now, in the second graph, it kind of looks the same. Points of it, like these points look the same. But you can actually see you get other places in between. So it's a little bit different when we multiply before we round. So I still get -1, -2. But when I plug in -1/2, it doesn't line up with the previous step. It has a new step point that it gets to. It gets to -1. So -1/2 is at -1. 0 is at 0. When I plug in 1/2, I get a step at 1. And when I plug in 1, I get a step at 2. Okay? None of these lined up. Okay? So if you want to see what's happening, plug in something between these. Like let's say I plug in 0.7, okay? What is 2 times 0.7? 2 times 7 is 14, right? So 1.4. Okay? What is 1.4 when the greatest integer function is applied to it? 1. Okay, so this one's going to line up with that one, right? Because they had the same output. So when I plug in 0.7, I'm getting something lined up with my 0.5. That means my step is right here before it jumps. Sorry. So this is what's happening here. So we said when a number was inside multiplying x, that it was going to do what? What did we say the b would do? So think back. I'll come back to the screen. Okay, we said that the b, if there's something in here multiplying x, it could do the reflection. We already talked about that. It also controls horizontal stretching or compressing. Okay? So we put a 2 in here. What happened to our steps horizontally? Did they get stretched or did they get compressed? They're shorter, right? So they got compressed. So putting this 2 right here was a horizontal compression. So it didn't get multiplied by 2 because normally they were 1. 1 times 2 would have made them 2 units long. What do you think the 1 got multiplied by? How long are they now? How long are my steps? 0.5, right? Okay, so horizontal stuff sucks, basically, okay? It's just like the h's and the k's. Look back at that original formula. K is super nice, right? It says plus 5, you go up 5. It says minus 3, you go down 3. You do exactly what it says, okay? A was super nice. You put a 2 on the outside, guess what? The steps are 2 units apart now, okay? If somebody put a 1/5 on the outside, the steps would be 1/5 of a unit apart. The vertical stuff, you basically do exactly what it says. The horizontal stuff is all screwed up, right? When this says x minus 2, do we move to the left 2? No, h is actually positive 2, and we move to the right 2. Well, guess what? This has a caveat like that too, something that's going to hang you up a little bit. It said 2, but we didn't multiply it by 2. We actually multiplied it by the reciprocal of 2, okay? So basically, our step length here got multiplied by 1/2. So what you need to try and get set in your mind is all the horizontal stuff is going to have some little component to it. Like the h is always the opposite of what you're looking at in the parentheses, right? With the b value, you always have to use the reciprocal, and that's going to tell you how long your steps are going to be. All the vertical stuff, all the stuff on the outside, super straightforward. All the horizontal stuff, not so much. Okay? All right? And it has to do with this whole, well, you do it before you plug it in, and stuff like this is happening to it, and that's why it's not working exactly how you think that it would work. Okay? Uh-huh. Okay, so negative 0.5 is going to get multiplied by 2. So it's going to be negative 0.5 times 2 will be negative 1, and then it won't get rounded. So that's why this is like a little more interesting. No, because the 2 is on the inside. It gets multiplied first. And that's why this is different than absolute value, and we can't just get the 2 out, because the answer ends up different if the 2's inside than outside. With absolute value, it didn't end up different. Okay? I plugged in 0.7 in between for us to try something in between since we only had new endpoints everywhere for you guys to see how the step was lining up. Okay? Till I got something that lined up with another point. Clementina? Uh-huh. So when I plug in negative 0.5, it gets rounded to negative 1, but then it still has to get multiplied by the 2 that's in front of the function after I've rounded it. So I plug in negative 0.5. The greatest integer functions brackets round that to negative 1 before I do any multiplication. Okay? Sorry. I don't have brackets anymore because I already did the rounding. Now I'm doing 2 times negative 1, and that's going to give me negative 2. Okay? Yeah, so it works out a little differently depending on where we're rounding. Okay, so the point is, if we know what the reflections do and we know what these numbers do, when someone gives us a hard problem, can we graph it without having to plug in and make this t-chart? Because you guys can see a lot of mistakes could happen, right? There was only one thing to do here, and we were still like, where do we round? What do we do? So, what's that?
So, say it's for the number three,
Uh-huh.
say it was 3,
Uh-huh.
2, and then another step, you're now like 0.5.
Yeah,
The step you like,
a third. It's always the reciprocal, yeah. Where it's like hard to graph like that. You could scale your graph differently if you wanted. Or maybe you'll get something where it's like 1/5, and when you flip 1/5 over, your steps will be 5 units long, or something like that. Yeah. Okay. So let's say I'm going to graph this. I don't want to make a t-chart. Look at all the stuff that's going on. How do I even plug in the right where do I know the endpoints are that don't have to get rounded? All this kind of stuff. So what I'm going to do is I'm going to try and separate it into that format that we saw. So I just know this number does this number does this, and then I can just draw my graph from what I know everything does. Okay? First thing you have to do is you do have to separate the 2 from the x, just like we did with absolute value. Difference is I can't get the 2 all the way out like we just saw. It's not the same. So I have to leave it in there. So it's like the B instead of the A when we looked at that format. But everything now is in a spot where we understand it's doing something. Okay? All right, so here's how I would graph. First thing I want to do is figure out my starting point for the greatest integer function. Normally it was at 0, 0. It's only going to stay at 0, 0 if it's not shifted anywhere. Has this graph been shifted left and right or up and down? Yes. Okay, I know that because there's things being added and subtracted. Okay, so the h value is what? 2, positive. And the k value is 1. Which means instead of the vertex being at 0, 0, I will shift 2 to the right and 1 up, and that starting point should be at the point 2, 1, okay, instead of 0, 0. So I'm going to go ahead and put that on my graph, 2, 1. Done. Okay. Now, normally when I draw my steps, once I have a point, I draw my steps to the right and make the open end point. The only time I draw my steps towards the left is if there was the negative on the inside, right? Is the only time my steps got flipped over horizontally to go the other way. Is that the case here? Is there any reflections here? No. So I don't have to worry about drawing my step another direction. And in the end, my step should look like it's going upward as a staircase, not downward. Okay? So I don't have to worry about reflections. Then what are these 2 numbers going to do here? So let's start with the 2. What is the 2 telling me about this step function? Okay, so Isabel's saying flip it over like 1/2, right? And what is that telling me about my steps particularly? What is 1/2? Courtney? Good. So this number in here, remember, controls the horizontal length of your steps. But the tricky part is you can't just use the number. You have to use the reciprocal, because all the inside horizontal stuff is crazy. So the horizontal length of our steps is going to be 1/2 a unit. So if I know there's no reflections, and I know my steps are 1/2 a unit long, I can go from my starting point right now, and I can draw a step that's 1/2 a unit long. Okay, there it is. Now, for my next step, am I going to go up or am I going to go down? Up. I want it to be the rising staircase. There was no reflections, so I just need to travel onward that way. Okay? How much up is then determined by the vertical stretching or compressing. Remember that this front number determines our vertical distance between our steps. Okay? Is the vertical distance between our steps going to be 3 or 1/3? 3. The vertical stuff, we just get to keep it the same as it is. So stuff outside the function like k and a, easy. All this crazy stuff, it says -2, it's a +2, this says 2, it's a 1/2. But everything on the outside, what you see is what you get. Okay? This said +1, we went up 1. This says 3, the vertical distance between our steps will be 3. So I know that I want to go up to draw my next step, but instead of just going up 1 unit like I do with the parent function, I'm going to draw my next step 3 units above this one. So where I ended this one, count up 3 units. That will be my starting point for my next step, and it's still 1/2 a unit long. Once you get 2 steps on your graph, you have the pattern, okay? But at least draw like 4 steps on your graph so I know you know what you're doing. Okay, you don't have to fill the whole entire graph every time. 1, 2, 3, but at least 4 so we know what's going on. 1, 2, 3. Sorry, that should be that one. So half a unit long because of this 2, 3 units apart because of this, and I started at 2, 1 because of this. So the only thing this problem didn't have in it was reflections, and those would just control the fact that instead of going 3 units above to my next step, I would have gone 3 units below if this was negative. If the 2 was negative, not only would I have gone 3 units below for my next step, but I would have drawn the steps going towards the left and not towards the right. Okay, but you have that for reference in your packet. So tonight your homework is 8 problems like this that are on the Cosmic Catalog page, the back of it. Okay, one comment. If yours looks like this one, so it depends on which version I open up here and they look different. The boxes or the blank spaces are supposed to be minus signs. I don't know why they don't get converted in the PDF document. Yeah, and I'll make a note on Canvas or I'll repost the equation. Yeah, just stay at the end and I'll print you guys. Or you guys can take a picture of it. Just know that the boxes are minus signs, okay? So 8 graphs tonight. Graph them, know that vertex point, that starting point, and know the changes you made, like any separation vertically, distance of the step horizontally, and any reflection.